Okay, we're going to look at how the EMF is induced in a Hall probe or a search coil and how that varies with angle. First of all, let's just remind ourselves what a Hall probe is. A Hall probe is a piece of semiconductor in which, when placed in a magnetic field, it will, and having a current flowing through it, it will cause, according to the left-hand rule, a movement in that current. And I'm just doing the left-hand rule now. We have a downward movement, so we're going to get a deviation due to the force induced on those charged particles, and there's going to be that deviation. And the deviation will in turn cause a voltmeter to give a readout. Of course, we know that the strength of the magnetic field, and we could probably go through the whole theory, but suffice to say that the voltage equals BVD, or in other words, the voltage is directly proportional to the magnetic field. So this is our magnetic field B. That's what a Hall probe does. And the other device we're going to use is a search coil. Now, a search coil is merely a series of coiled wires, usually on some sort of stick, and when a changing magnetic field is felt by it, it will induce a voltage, an alternating voltage. And the way that and it only occurs if there is an alternating magnetic field. And that makes sense because we know that the EMF induced is going to be minus d phi by dt, which is dBA by dt. So the magnetic field here and the voltage again are proportional. Well, it's going to be dependent on the rate of change of how quickly that's moving. Nonetheless, we have two ways, the voltmeter here and the voltage there, of detecting the size of the respective magnetic fields. Okay, let's think about how the magnetic field changes, of course, with angle, because, I'm just going to move to another slide, because if we do have a magnetic field acting, and we know we have this conductor, we know that in that projection we have a maximum effect from the B field, from the magnetic field. We know also that we get a minimum effect when it's parallel to. Good. And that's probably due to, we can argue this, we could discuss this both ways. We could say how much of the conductor is projected horizontally if we know that that's at a max. Or we could say how much of the magnetic field is projected to the perpendicular of the conductor, whichever way you prefer to talk about it. So let's just take an example where we're somewhere in between. And we have our angle theta. Then what we could say is that this distance here is the horizontal projection. And so therefore the opposite over this, that's the opposite, and this is the hypotenuse. We can say to ourselves that the magnetic field felt is going to be the initial magnetic field sine of theta. because not only do we have, so I'm looking at the component which is parallel to the magnetic field, which is the same as saying how much of that magnetic field is at a component horizontal to the conductor. Good. Needless to say that when we are sitting at 0 degrees, we know we're at, so let's just make sure this is correct, theta equals 0, sine theta is 0, hence this is correct. Whereas when we're sitting at theta equals 90, sine 90 equals 1, so therefore we're working to this point because we're at 90 degrees, and again, that gives us our maximum. Excellent. So what we're looking to do is we're looking to move, we're looking to have a magnetic field set up and then slowly move our search coil or Hall probe through a range of angles to see what happens. So what's our independent variable here? Well, our independent variable is the angle. What we're going to change is the angle in degrees, and then we're looking for voltage. And we're looking for once, twice, 3 times, and an average, and then we're going to plot that voltage average against the voltage against the angle. And hopefully what we'll see is we'll see the beginnings of a sine curve coming out. So that's hopefully what we'll see. So let's see. So let's just see the setup before I show you the real practical. There we have our horseshoe magnet. We have our Hall probe in there, into the Hall probe control unit, and then my voltmeter out there. And I'm looking to rotate this around a certain number of angles. If you imagined that this was my magnet in 3D, there was my Hall probe, we'd be looking to rotate this through the magnetic field. So now you've seen the setup, let's have a look at the video of this actually happening. Here it is, ready to upload. And I'll let you see me do the video. In reality, let's just zoom that up.
Okay, here is the experimental setup for working out the amount of magnetic flux there is flowing through, there is in this horseshoe magnet. There are 2 ways to set up the experiment. I'll show you the next one in a moment. This one uses a Hall probe, and I'm not sure whether you can actually see that very clearly. However, it is inside here a small microchip, a small semiconductor, sorry. No, there we go. Maybe that's a bit better. A small semiconductor that when a magnetic field is going through it will cause an induced Hall voltage, which the theory is in, we'll deal with in another video. So what I'm looking to do is I'm looking to place this inside my magnetic field, and it will induce a voltage. Let's just see if that is the case. There you go, 3 volts, and as I move it away, 0 volts. My Hall probe is placed into this meter here, which just simply interprets the voltage and displays it. I have this 0 set meter as well, so when completely away from a magnetic field, I turn this and make sure I'm working off of 0. Otherwise, it might be detecting other magnetic fields, and I'm just interested in the magnetic field in the horseshoe magnet. So outside of it, I set it to 0. Good, so this bit we can pretty much ignore. This is working as a voltmeter. So the idea of the experiment was to look at how different positions in the magnetic field yield different Hall voltages. And in order to do that, I placed a protractor on the top of this horseshoe magnet. And when placed in the horseshoe magnet, we need to be careful. Not only is this orientation important, but also that orientation important. So if I were to place it like that, it's 3.3. If I were to move it down a little, we're at 3.17. So we need to make sure we keep that correct each time. Similarly, often Hall probes have a maximum they run at. So when I start my movement, you're seeing it's not moving at all until I hit a point where it's below 3.3, which is the maximum Hall voltage produced. So make sure you're not exceeding the maximum in its maximum position, otherwise you're not going to see a variation early on. So how did I set this up? Well, I also know that the Hall probe in there is not going to be perfectly aligned with this arm. So what I did was I placed it at a position where I'd get no flux at all, no Hall voltage, i.e. at 90 degrees. So I moved it until I got to 0, and then I adjusted the protractor so this was lined up with 90. Just move that slightly, it's just slightly off. So at 90 degrees there, that's it. Or indeed, when I say 90, it depends whether we're usually using a cosine or a sine of that angle. Nonetheless, at 90 degrees, I was looking for 0, which it is. So therefore I readjusted this. And then I moved, placing that in there, I held the arm against the protractor, and therefore I knew that I was getting this projection correct. And then I took a reading, I moved by 10 degrees. So took a reading, wait for it there. Then I moved by 10 degrees, took another reading, moved by 10 degrees, took another reading, and we can see that this is diminishing, this is decreasing as I go around to the different positions until we get to a point which hopefully we have 0. And then we do that 3 times. And then we look at how the Hall voltage compared to the angle compared.
It's probably worth saying here that I did say that I would be taking, let me draw in which position was at 90 degrees. I said that this position here was 90 degrees and that I was working from this position from 0 degrees. However, if you imagine to yourself what's going on inside this arm, is there's a little semiconductor which sits that way. So if it were placed in here at what I thought was 90 degrees, that would actually be sitting across that magnetic field, which would be going between them. So subtle point here is that should actually be 0 degrees, and this one should be at 90 degrees. But nonetheless, we get a series of results. Let me give you a quick look at what the results look like. There they are. I'll just try and zoom them up. We have our voltage, the angle from 90 down to 0, our voltage, which has an average, of course, there. And you can see that as we move from 90 degrees, a maximum, we have a minimum at 0 degrees. So let's take a look at how the graph looks. Here, of course, is the graph. I'll just pull that up. And what we should be seeing is something which looks very much like the beginning of a sine curve. I need to just add in there the axes, the angle in degrees, and Hall voltage versus angle, and we're looking like a lovely sine curve. So hopefully that will prove that the magnetic field, sine theta is equal to B. Excellent. Now I did promise you that I'd show you how to do it in a different way. So let me let me get to that page and introduce to you this next diagram, which makes use of a search coil. So here is an alternating current low voltage supply, and that is driving a circular coil. So I have an alternating current inside my circular coil, which of course will be producing a magnetic field, and the magnetic field will be alternating back and forth. I have a search coil, which again is a coil of wire, and that's fed to an oscilloscope, which gives a printout looking, gives a signal looking like that. In other words, it's observing that change in magnetic field because the EMF in the search coil is equal to d phi by dt. There is a minus sign in there, of course, which is the same as d by dt of BA, the rate of change of magnetic field times area, which is flux. The height of this, or should I say the peak-to-peak reading divided by 2, because that's a good technique for oscilloscopes, will equal the EMF. And as I rotate that coil, or indeed if I want, I could rotate this. However, if I rotate that coil, we are going to see that signal diminish. Not the frequency, but the amplitude of the signal diminish, or the peak-to-peak will diminish, implying that the EMF has decreased because the magnetic field has decreased, hence a measure of magnetic field. So this technique is one in which we can again explore whether the magnetic field produced in here and the magnetic field felt, because I should be specific and say that that magnetic field felt is B sine theta, A, varies with the angle. So here is the video of that, practical. Not that I've taken many readings, but nonetheless you can see the setup. Just loading the video. Let's get that larger.
Okay, here's my next setup for working out how strong the magnetic flux is in the middle and how it varies with angle. What I've got here is I've got a signal generator, and the signal generator through the yellow cables are driving an alternating current around this coil, this outside coil. Then what I have is a search coil placed in the middle, which is just another series of coils, but that is then attached into my oscilloscope. So the changing magnetic field, or the changing flux that this one's producing through here, back and forth, because of course we have our right-hand grip rule, the magnetic field, and as the current turns around the magnetic field, so we have this changing magnetic field back and forth through there, will cause an induced EMF in the search coil, and that will be shown up here. Now, of course, the rate of change of magnetic flux linkage is equal to the EMF. So if I increase the frequency of my signal, not only is it changing more frequently, but also I get a higher induced EMF than if I decrease the frequency. And of course, what we're looking for is we're looking for how this angle, as I move this, compared to the search coil, changes the induced EMF. What you're looking for is you're going to want something noticeable here for each small angle. So it might be necessary to turn up the frequency and have a higher frequency, and it's a higher EMF, And so therefore you're going to notice more change as you turn the search coil or the outside coil, but you're looking for that relative angle between the two, which it is diminishing nicely. And of course, when we hit parallel, it's sort of there. I'm not quite at 90 degrees though. Nonetheless, I think we can see a nice plot there. We can actually take angles and positions by, if you want to, just draw on the table a center point and each angle, subsequent angle. And of course here you're looking to take peak to peak and halve the peak to peak, because you can, of course, move the position of the signal. So at a position, peak to peak, half the peak to peak will give you the induced EMF. Of course there's going to be a scaling depending upon what position you have your voltage gain on. Here it's on 20 millivolts. But nonetheless, you should see a nice plot showing a maxima through to a minima.
Okay, so there's the other setup. You've seen two ways in which to work out the angles. I prefer the Hall probe because it's just a little bit easier than measuring this quite fuzzy trace. Okay, results are on the link below.